So now we know how to find the magnitude of G field strength. And the way we do it is by using the equation G is equal to big G, the gravitational constant, times the mass, the source mass m, over r squared, where r is the separation distance. But G field strength is a vector, so it doesn't just have that magnitude, it also has direction. So what we'll see now is how to find the direction of the G field strength vector. So let's say we have this random point P. The way we find the direction of the G field strength at the point P is you imagine placing a test mass at point P, right? A small test mass. The test mass would get pulled in like this. The force would be directed in toward the source mass. Well, if the force is pointing in like that, then the G field strength points in the same direction. And that's the general rule we use. The direction of the G field strength at some point P is the same as the direction of the gravitational force on the small test mass that we place at point P. So if we took this point over here, then the force would be directed in to the right toward the source mass, which means the G field strength would also be directed in the same way to the right. And at this point P, G would point in toward the source mass. Okay? And if we took some farther point P, which was farther away from the source mass, well, at this point, the G field strength will also be directed to the right. That's where it will point. But because we're farther away, the value of R is larger, and the G field strength magnitude is smaller. So the arrow will be smaller, since the magnitude of the G field strength is smaller. And we could actually imagine filling all of this space around the mass m with these arrows, these vectors, representing the different G field strength at each of those points. And it would look like this. So what we have here is a region of space, which we call a field, and at each point we have a vector represented by an arrow. So we have a field of vectors. In fact, we call this a vector field. So gravitational field is the first example of vector field, of vector fields that we will see. Now imagine we have the source mass here and test mass here. The equation for G field strength is this. But because there is a force of gravity on the test mass, we could write it as this. Here's the equation for the gravitational force on the test mass, right? Where m, big M, is the source and little m is the test. Notice the only difference between these two equations is the m sub test right here. Right? So this factor is absent from the top equation, but otherwise, the right side of this equation and the right side of this are the exact same. So what if we take this second equation and we rearrange by dividing both sides by m sub test? Well, then we get, if we divide both sides by m sub test, on the right, the test mass cancels out, and what we're left with is this. And if you look, you see that the right side of this equation on the bottom is equal to the right side of the top equation. So this equals this, which equals G. And in fact, what we have here is the very definition, the true definition of G field strength. G field strength is actually defined as the force on a test mass divided by the test mass. The gravitational field strength at a point in space therefore is defined as the force per unit mass produced on the small test mass placed at that point in space. So for example, if our mass is measured in kilograms, then G field strength is defined as the force per kilogram produced on a small test mass at the point in space. So here's how we can think about this. Imagine we have some giant, huge source, right, which is the blue here. And here is the test mass. Now, there is a giant gravitational force produced on the test mass. But we could take that force, and instead of thinking about it as acting on the entire test mass, what if we split my test mass here into 1 kilogram chunks. Each kilogram chunk would feel an attractive force, and each would get pulled by the source. And the definition of G field strength is the force per unit of mass. So one way to think about this conceptually is it basically tells us how strongly does the source pull on each kilogram of mass in the test mass. And that's what G is equal to. Right? It's how much does it pull per kilogram of test mass in the test mass. And of course, we see here, finally we can realize and understand why it is that the units for G are newtons per kilogram, because force is measured in newtons and m, mass, is in kilograms. So the definition of G field strength is G equals F over m, where m is a small test mass. Right? Imagine we place a small 1 kilogram test mass at some random point P, separated 1 meter from the source, like this. Right? And we measure the force on this test mass to be 0.002 newtons. Right? And we can easily calculate the value of G. It'd be the force, 0.002, divided by the mass in kilograms, because it's the, we have to convert to kilograms, the SI unit. And this gives us a value of G field strength equal to 2 newtons per kilogram. If we change our test mass here, right? I'm not gonna show it, but imagine we put a bigger test mass at the same exact point, and now it's a 4-gram test mass. Well, you might expect that the mass feels a stronger force if it's larger. In fact, we could even measure it, and what we would see is that the force on the new, bigger test mass would be 0.008 newtons. So if we calculate G again, we put in 0.008, we divide by the mass, 0.004, and we get the same value, 2 newtons per kilogram. So swapping out a larger test mass did not cause the G field strength at this point to change. In fact, the G field strength remained the same. The only thing that changed when we plugged in a larger, when we swapped out a larger mass, the only thing that changed was the force, which increased. So what this indicates is that G field strength is independent of the test mass m. It doesn't matter what size test mass we place here, as long as it's relatively small, we will find the same value of G no matter what mass we use. So the way we say that in physics is we say the G field strength at some point is independent of the test mass. You might be wondering, why is it that the definition for gravitational field strength, why does it refer to a small test mass? Well, in fact, we have to use a small test mass, and here's the reason why. We want the test mass's gravitational field to be negligible. Now we're putting this test mass here, but remember, every single test mass and source mass, every single mass in the universe has field lines. It has a gravitational field, but we haven't been drawing it around the test mass. Right? Really, we should draw the gravitational field lines because every mass has field lines. And in fact, if we didn't use a small mass, if we used a large mass, then these field lines would be noticeable and the field would be noticeable. And this test mass could start pulling noticeably on the source mass, and it could cause the source mass to start moving. And this would interfere with the source mass's G field. So we want to take away those field lines. We want to make them disappear. We want to be able to ignore them. And the only way we can ignore them, the only way that this is acceptable, is if the test mass is very small compared to the source mass. So that's why the definition for G field strength refers to and requires, in fact, a small test mass. Newton's second law states that an object is accelerating due to gravity when that's the only force on the object. In other words, F net equals ma, and F net could be replaced by the gravitational force. So if we rearrange for acceleration, we get this. But this is strikingly similar to the definition for G field strength. See this? In fact, both are equal to F over m. And this force here is clearly Fg because it's a gravitational force. So this raises a question. Are these things simply equal, acceleration due to gravity and gravitational field strength? Are they just equal? Are they the same thing? What's the connection here? Well, in fact, these are two totally different concepts. They just happen to work out so that it happens to work out so that the two are equal. Here are some differences we must understand. First of all, acceleration has units of meters per second squared, and it describes conceptually the rate at which an object's velocity is changing. So in order to have acceleration due to gravity, there must be a falling object. Right? Acceleration describes changing velocity. Gravitational field strength describes something totally different. Its units are newtons per kilogram, and it measures how strong a gravitational field is. And here's one way of really emphasizing the difference between these two. A point in space can have a non-zero gravitational field strength regardless of whether anything is actually accelerating, whereas an object can only accelerate due to gravity if it's actually falling and accelerating. Now, one of the things we must be able to do is derive an equation for the gravitational field strength at the surface of a planet. So here is that derivation. Be able to reproduce it as shown. We know that the G field strength at the surface of a planet is defined as the force on a small test mass at the surface divided by the test mass. So here m is a small test mass at the surface. But according to Newton's universal law of gravitation, the force of this test mass, the force on this test mass is equal to big G times the mass of the planet times the test mass divided by their separation squared. Now we know that the separation distance r is the distance between their centers. So imagine here is my planet and here is the test mass. This test mass is so small compared to the planet, it might as well be a dot. And of course, if it's a dot, then the distance between their centers is simply the radius of the planet. So r here is the radius of the planet. I'm going to plug in r sub planet to represent that. And then what I'm going to do is I'm going to plug this equation, the right side, I'm going to plug it in for F on m. When we do this, here's what we get. G at the surface is equal to big G. Look at this. There's a little m here in the numerator and a little m in the denominator, so they cancel out. We can simplify and write the equation like so. Be able to derive this equation, which gives us the G field strength at the surface of a planet. So, just like I said, using the equation we can find the G field strength at a planet's surface. I want you to try and plug in the mass of the Earth, right? Using this value, plug in the radius of the Earth, and if we calculate G, little g, what we find using this mass and this r is we find it is equal to 9.81 newtons per meter. And in fact, it does equal the acceleration due to gravity. So give it a shot. Use the equation on the last slide and use these values to derive the fact that G is 9.81 at the surface of Earth. And notice in the equation on the previous slide, there's no little m in the equation. So down in the final equation here, little m does not appear, which means the gravitational field strength at the planet's surface is independent of the test mass. And that is nice and pleasing because it agrees with the fact that all objects, regardless of mass, have the same free fall acceleration at the Earth's surface.